Let's pause this. Yeah. Hi, everybody. Since it's 5:30, I think I'll start on time. So anyway, just to let you know, this session will be recorded and then it will be uploaded on YouTube. So if you are not able to join me for the full 1.5 hours, right? You can still tune in on YouTube lah. Okay. So all of you should be able to see the meeting chat. The worksheet is there if in the link given to you already if you have not yet obtained the worksheet. Today we'll be doing a revision of Reactivity series and chemical energetics for Sec 4 chemistry. Okay, hold on. Let me put away the timer. Okay, before I start, I'll give you a short introduction of myself and the company. Um, so I'm Miss Abigail, if you don't know me or if you have seen me like for the first time today. Today I um am here to actually teach you online. Wait, let me take a look at the. Oh, okay. Um, sorry. I think. Eh, give me a while lah, because I think some people they don't have the worksheet. Hmm. XH, you able to see the chat? Okay, so as I was saying, I am teaching actually Sec 3 and Sec 4 chemistry in OVERMUGGED and as well as additional mathematics. Fun fact about me is that actually I just gave birth to a baby boy last year. So I just came back from maternity leave in January this year. Yeah. So I'm happy to be back again teaching besides feeding my son. Besides that, I like to drink coffee and I like to take photos also. Yeah. Okay. So overmarked over here, we have a group of students that we passionately teach. We have uh 70% of our students achieving distinction at O levels and A levels. So more will of course also obtain B3. So typically, we have some students who actually join us quite late, and from a failing grade to actually obtain B3 is also a feat here lah. Okay, and we have about 8 centers, actually two, four, six, eight, seven. Sorry, 7 centers. In Overmarked, we actually shifted away from Woodlands last year. But anyway, we still have uh centers across Singapore, and these are our classes at all the different centers just for chemistry. We have about close to 20 classes lah. Yeah. So if you're interested to know more, you can scan this QR code. So what do we do in class? Okay, so we have notes, we'll go through notes and then we'll have also worksheets. Uh, Time to time, we also revise for WAs, on top of this free WA revision. Okay, and then since we are in the Sec 4 year, we will also be carrying out practical sessions and also mock exams for the students here. So I just show you some clips of what our students have done for practical last year. So over here, I have a student carry out titration. Okay. So the color of the solution is blue, and then it will actually change colorless. Um, so at Overmark, we also allow our students to practice, have more hands-on, on top of what you all might have in school. Okay, and then this is our QA practical. So students have free rein to actually practice on their own. And then over here, we have the test for a particular anion. I don't know if you are familiar, if you are tested for QA. So if we are heating up this solution, and if you look closely, there is aluminium foil. Anyone wants to make a quick guess what this anion is that we are testing for? And I add aluminium foil. Just a quick quiz. If you can type in the chat. NH3? Okay, that's the gas. The gas is NH3. But if I want to test for the anion, and if I added aluminum foil, yeah, ideal is to test for nitrate. Okay, when we add sodium hydroxide, heat in the presence of element foil. So if we test for ammonia, okay, then that is nitrate ion. Okay, so that's a short quiz for you. At the end of the lesson, I'll give you a QR code to do a review. So actually, if you have the time to do a review, I will choose five of you based on the list that I received. So there's like your email address or your phone number. Okay, I'll give you a set of notes for upcoming topic of electrochemistry and a limited sheet of the periodic table and our cheat sheet. Okay, so just stay tuned to that. Now I'll move over to the notes. So does everyone have this? Give me a moment. Donna? Yeah. Okay. So you should be able to find the worksheet in the chat. Okay. If you don't have it, please let me know. Otherwise, I'll start right now. Okay, so for Reactivity series and energetics, so I'll be doing Reactivity series first. Okay. Okay, Ria. Okay, here. Right. Is this the same Ria that I taught last year? Okay, so for Reactivity series, right? Learning objective over here, number one, we need to know some of these metals and list them in order of the reactivity. So it is in this table here. Okay. So some of you have different ways of memorizing. That one is up to you. Like please stop calling me zebra, etc. All right. I want to focus more on the basics. So for reactivity of metals, we are looking at metals having very few valence electrons, if you recall in atomic structure. Hence, they will typically need to actually lose electrons, right? And that linking to redox. So some of you, if you're testing on redox, this is oxidation. So they will undergo oxidation. Okay. And in the second round of redox, we also learn about the different agents, reducing and oxidizing agents. Okay, so typically metals are therefore reducing agents because they can undergo oxidation. All right. So these metals here, okay, are placed in the reactivity series according to their reactivity. So from the most reactive, potassium, all the way to silver, which is the least reactive metal here. Hence, if we then compare, right, most reactive metal, okay, now I can say that it will undergo oxidation the most readily, and therefore it is actually the strongest reducing agent. Okay, if you have ever encountered questions like that before, then I would help you to also write this down here at the side. So the reducing power of these metals essentially will decrease down the group. Okay. Um, for the first four metals, right, see them as actually group one and group two metals. Then these are exactly the metals that can only react with cold water, right? In the solution, a result of that would be an alkali. So metal hydroxide here, okay, will be the alkali. So then if you learn periodic table, the first two metals, group one metals, right? Remember they are called alkali metals for a reason. And then if you react them with water, they will produce an alkali, and then H2 gas will be produced as a result. So the rest of the metals below in the Rayleigh series, they don't react with cold water. Okay, but once we bump up the temperature, we increase the temperature, right? And now instead of cold water, we have steam. Okay, essentially, now rate of reaction. You learn that higher temperature increases the rate of reaction. So therefore, now more of the metals can react with steam. Okay, so not just group one, group two metals. So in fact, for group one, group two metals, right? For potassium, sodium, and calcium, we typically don't react them with steam because it's basically just too dangerous. They do react, okay, but in the syllabus, we will just focus on magnesium, as the metal that reacts with steam. Okay, magnesium reacts very slowly with cold water. So once you increase the temperature, it reacts very readily or even violently with steam. Okay, then in this case, the product form will be a oxide instead of hydroxide. So at the high temperature, actually, the hydroxide will decompose into the oxide lah. Okay, H2 gas will still be produced. Then the cutoff point here is actually iron. So below iron, which is lead onwards, these metals don't react with steam. Okay, and the last one for the reaction with acid or hydrochloric acid per se. So acid plus metal gives us salt and hydrogen. You learn this in acids and bases, right? So in this case, we will bring in where the position of hydrogen is, and we always say that metals above hydrogen can react with acid. Metals below hydrogen, which is copper, silver, and even gold, they won't react with acid. Okay, so all of these reactions here, if you actually now focus on water, steam, or even acid, okay, just going a bit to the redox part of the reactions here. So for water, H2O, or for the acid, so specifically H plus ions. Okay, give me a moment. Steam is the same as water vapor. Technically, water vapor can exist at any temperature between room temperature and uh, the boiling point. Pretty. Yeah, so quickly ask the question. Is steam the same as water vapor? Steam is specifically at 100 degrees Celsius and above. Okay, water vapor, water can evaporate any temperatures between melting and boiling points lah. Um, so as I was saying, I wanted to focus on the oxidation state of hydrogen. Okay, so hydrogen is actually +1. And then when they all produce hydrogen, which is H2 gas, right, they actually showed a decrease in the oxidation state of hydrogen, now 0. So this itself is actually reduction taking place. Okay. So then when you look at the metal alone and the compound that it forms, then the metal will undergo oxidation. So all these reactions are essentially redox reactions. Okay, acid metal, metal steam, and metal water reactions. All right, we'll move over to the next learning objective, which is the reduction of the oxides now. Okay, by heating with carbon or hydrogen. So here it's in the presence of heat. So if we go down, I have the metals, yes. Okay, so now when I look at the oxides, of course, I'm going to give you the formula of the oxides. I'm not going to just give you the metals. So for these oxides, I want you to pay attention to iron. So for iron, because of its variable oxidation states, it will have FeO and Fe2O3. Okay, so for the way that we obtain the metals from the oxides, when we heat the metal oxides with carbon, all right, so only metals below carbon can undergo this reaction here. So therefore, it will be zinc, iron, lead, copper, and silver. Okay, so reducing by carbon, or carbon monoxide, we can actually obtain the metal. Okay, from the metal oxide. Again, this is also a redox reaction. Because I think if you just see reduction by carbon, so carbon actually would gain oxygen. Okay, so this is redox reaction. And then for the reduction by hydrogen, which is H2 gas, so here we will basically just skip zinc. If you look at the pattern here, okay, so for carbon, we will be able to obtain all the metals that are lying below carbon from the oxides, but for hydrogen, it will be skipping zinc. So it will be just iron, lead, copper, and silver. Okay, so over here, we will have hydrogen as the reducing agent, and then we will form steam and water vapor. Essentially, the oxygen is sort of like transferred to hydrogen, okay, to form H2O here. So this will be the notes section for this learning objective. Okay, so next we have 2 questions, just very short MCQs. All right. If we take a look at question 1, which metal displaces hydrogen from HCl but not cold water? Okay, so over here, displacement of hydrogen from HCl is actually the reaction with hydrochloric acid. So remember, we are looking at metals just above hydrogen in the reactivity series, and then not from cold water. So if a metal displaces hydrogen from cold water, we are looking at, again, the group 1 and the group 2 metals, which are potassium, sodium, calcium, and magnesium. Okay. So, but the keyword here is not. So I should not choose any of these. And magnesium is over here. Okay. So for above hydrogen, copper is below, silver is below. Then that's where we will obtain B as the answer. Question 2. So hydrogen is produced by the reaction of metal X and acid. So when we encounter this question once again, it's similar to this question, right? In other words, I will eliminate any options that would have copper, silver, gold because they are below hydrogen in the reactivity series. They cannot produce hydrogen if you add the metal to acid. Okay, so over here, we will eliminate 2. So usually, as you eliminate, straight away look at the 4 options, right? Eliminate A and C already. So now we'll be left with 1, 3, and 4. Okay, so we will take a look. 3 is actually in the answer, right? Because it's an overlapping option. So now when the same gas is passed over an oxide of metal Y, okay, so remember this is the cutoff point, iron and below. So lead, iron, copper, silver. Okay, over here, I can only reduce the oxide of iron, lead, copper, silver. So lead, silver, iron, calcium, no. All right, so when we eliminate 4, then our answer will be B. Okay, so that will be uh, this question's answer. All right, then let's move on to the next learning objective. So the next one that we will also consider would be the reaction of a metal, okay, with another compound. So the compound could actually be a salt solution or an oxide. Okay, so this is actually displacement. If you just read the learning objective, right, what is it? What is it talking about? So over here, describe the Rayleigh series as related to the tendency of a metal to form its positive ion. So this is again still on the reactivity. Okay. So it's not stated, right? So you must know this is actually displacement. So if you have also learned periodic table, displacement is also occurring in group 17 metals, group 17 elements. Okay, where a more reactive halogen will displace a less reactive halogen. Similar reaction. Okay, so for metals, more reactive metal, right? Now I need to be very familiar with this. More reactive, right, actually means that the atoms, okay, will lose electrons, then to form the cations. So in the reaction, if the metal atom loses electrons, the electrons don't just go into the solution. There has to be an electron transfer, right? So the cations of the less reactive metal, which is in the solution, will now be the ones that will gain the electrons to form atoms. So in other words, electron transfer, right? We are looking at a redox reaction again. So again, we see an overlap in Rayleigh series and redox reaction, these 2 topics. So even though I did not specifically say I want to cover redox, right? So these are some of the things that we can also link to the other chapter. Okay. So one example over here for displacement reaction is if I actually place this iron nail into a solution containing copper 2 ions, right? It looks a little bit bluish, or it should appear blue. So I could probably say that this solution is quite of a low concentration of copper. That's why it doesn't look too blue. Okay, so over time, let the iron nail sit in. You'll find that reaction takes place. So how do I describe what I see, right? So we actually see that the nail becomes bigger in size, sort of. So and then if we look at the color, so copper is actually it actually appears red brown here. Okay, and now the solution also changed color from blue to actually green. So green because of the presence of iron 2 ions. All right, so this is actually where we can also explain from our prior knowledge or theoretical knowledge that it's because from the Rayleigh series, iron is more reactive than copper. So for some of you, from what I know, so just last Wednesday, the VS students told me I can't just say more reactive. Their teacher wants them to actually write down iron actually has a higher tendency to lose electrons. Okay, so if your school requires you to write something more, please do that. Okay, but generally, we compare the relative reactivity first of the metals if we know what they are, and then we can then explain. Okay, therefore, iron can displace copper, right? So see how we can actually just bring in the observations together with the explanation. The solution was blue, and then it actually now formed the red-brown copper metal and the green iron 2 sulfate solution. Okay. And usually, what will accompany all your answers would also be the chemical equation. And from here, sulfate ions are the spectator ions. Cancel out, we will have the ionic equation. And from there, you have also probably have done this exercise of splitting this ionic equation into two half equations, right? And over here, we can identify this first half equation as a oxidation reaction because there's an increase in the oxidation state of either iron, or we can see this as the loss of electrons. Okay, so the other half equation will be the reduction half equation. Okay. So in terms of the application part of displacement, right? So we can have either known metals and we know where they are relative to each other in the Rayleigh series, or we could also have unknown metals. Okay, so example in these two tables here, we have actually like an unknown metal X, or let's say chromium, right? So we may be tested on all these other metals not included in the Rayleigh series, but it's from the observations that we are given. Okay, so again, I'll write this down. It would have been the color change of the solution. Specifically, I mean, if we looked at the solutions of transition metal solution salts. All right. The other one would be the color of the metal or solid that is depositing on the pure metal. Okay. On the pure metal added. All right. So I have actually these two tables for you here. My aim is for you to see that actually, there's a bit of difference in the presentation of the tables. So whenever you are encountering this type of questions in school, right, or your exam or test, always see the metal first and then look at the solution, number two. Okay, so you can visualize as in this type of diagram here. I place the metal into the solution. So if I see any observation, it means that the metal that I added is more reactive than the metal that is present as ions in the solution. Okay? So for the second one, the second table, same thing. I look at the metal that I'm adding and then I refer to the solution. So you do not mix up. All right? Because sometimes if you panic, right, then how do I read? How do I read? Okay, so just be very clear. Look at the metal added, then look at the solution and then compare. Okay. So the observations can come in the form of like the color change and the solid and the color of the solid formed, or essentially just no visible reaction. Okay, or if not, the question will just say, okay, this metal is being displaced. In this case, the whatever metal that's displaced is from the solution itself. So if you take a look at this, means X is more reactive than copper. So copper got displaced out and copper would have formed. All right. So these are the two things that you need to take note of. So if we take a look at all these questions here, I think I will not go through 3 and 4. They're pretty simple. You should be able to do this quite easily. Okay, so for question 3 is just knowing where iron and lead are in the Rayleigh series. Um, I'll give you the answer on the next page. Okay, for question 4, here we have a few reactions. This one is displacement. All right, so you can tell which is more reactive than the other, copper or P. All right, then the second one is in the reaction with acid. So metal plus acid reaction. Sorry. No, 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 no. My goodness. Same, displacement. I am so sorry. It's the last one that is the acid metal reaction. Okay, metal here, H2SO, acid here, H2SO4, sulfuric acid. So metal plus acid reaction. Okay. Then just a reminder once again, when I see metal reactive acid, this metal just has to be above hydrogen. All right, it cannot be like the one of the least reactive metals of copper, silver, or gold. Okay, I want to focus on 5. 5 is a very interesting question. So if you take a look at this table here, I have zinc metal added into 2 solutions, A and B. So the initial mass of the metal, the zinc metal, was fixed at 10 grams. Okay, then after half an hour, the mass of zinc appeared to drop for A, but increase for B. So what could be the reason? If the mass decreased, okay, we need to remember, okay, that this solution will react with a metal. Okay, and what could result in the decrease in the mass? It will be, if you compare over here, salt solution, acid, salt solution, acid. More likely, acid reaction with the metal. Okay, why? Because acid plus metal will give us salt and hydrogen. So the hydrogen gas is going to actually be lost from the surroundings. The metal will react completely. Okay, but in this case, perhaps I will just explain that the solution is very dilute. So the metal reacted so slowly that it only decreased in like 0.5 grams. Okay, for B, right? Why would the mass increase? Okay, so here it will be due to likely displacement. But if I get you to look at now the reactions of B and C here, what you will realize is that I have iron 2 sulfate and silver nitrate. Okay, so remember, zinc metal is more reactive than iron, is more reactive than also silver, Ag. So in that case, displacement can actually take place promptly. Okay, so then what would you choose, B or D as the answer? We will need to study in depth over here. So for iron 2 ions and silver ions, when they react with zinc metal, so once again, remember, so the more reactive metal, which is zinc, will undergo oxidation. It will lose electrons to form zinc ions. And then Fe2 plus will gain electrons to form the pure metal ion. Okay, and zinc ions will form as well. Silver ions will form silver metal. Okay. Ionic equations, not quite balanced for the second one yet. First one is balanced because we look at the charges here. 2 plus, neutral. So overall is 2 plus. This side here, 2 plus neutral, also overall 2 plus. So balanced. Second one not balanced, silver plus, zinc 2 plus. Right? So what we need to do is just add in the coefficient, the big number 2 in front of silver, ions, and silver metal. Okay. So if we now consider 1 mole of zinc reacting. Okay, let's just say this is just 1 mole first. I fix it to be 1 mole. So if I have 1 mole of zinc reacting, it will react with 1 mole of iron 2 ions. So all of them will all be 1 mole. Okay, either reacted or formed. So if we now look at the mass of, let's say, zinc that reacted away, if you refer to the periodic table, I have it on the very last page. Let me rotate this. Okay, so zinc is having a mass of 65. All right, and then iron is 56. So going back to that page again, so here. So this 1 mole of zinc, let's just say I'm just using 1 moles. So the mass is of course going to be bigger than this 10 grams here. Okay, and for iron, 1 mole would be 56 grams. So in other words, if you just see if 65 grams of zinc reacted and 56 grams of iron formed, this will actually result in a decrease in the mass instead. Okay, but in our example here for solution B, the mass actually increased. So this will not be the answer. Right, and I'll just show you for the second one. For the same 1 mole of zinc, 65 grams, then it will actually produce 2 moles of silver. And for silver, the relative atomic mass is actually 108 over here. Okay, so 2 moles, 2 times 108, then that will actually give us 216 grams. So now you will be able to see, right, that 65 grams then increase, 65 grams react away, and then 260 grams of silver will form. So this will result in an increase in mass. So the answer for this question is D. Okay. We'll move on to the next page. Sorry, not hello over here. I was just testing out just now. For this question 6, I'll just show you the answer here. Okay. So when you encounter this again, I have two different metals, Y and Z. All right, so look at again the information of the question. This is the given information. Deposit is actually being observed on the metal strip. So the metal that I added is more reactive than the metal from from the solution here. So copper is more reactive than Z, magnesium more reactive than Y is more reactive than copper. Okay, from there, you'll be able to actually obtain the reactivity of the metals. Then always read the question also. Do we want to start with the most or the least reactive? Okay. For part B, which are the metals that are able to react with aqueous hydrochloric acid? So metals, multiple, we'll choose magnesium and Y. Okay, because again, remember, this copper metal doesn't react with dilute acids, so that will also not be able to. Okay, so choose any metal that is less reactive than copper for C part 1. All right, then that gives us either silver or gold. But say if you use gold, then in your next part, right, perhaps you might have some difficulty in writing out the formula of the ion. So what I'll suggest is, okay, scratch back, don't write down gold, write down silver instead. So choose what you are more familiar with. Okay, so silver ions is Ag plus. Gold anyway is Au plus. All right, for gold ions. Okay, Then all in all, similar to the earlier MCQ, very importantly, please balance the equation here. Okay, such that the charges are equal on left and right hand side. Okay, so this should be a relatively simple question lah. All right, we will move on to the next page. So moving on to now the compounds, okay, of the metals. So for the carbonate specifically, if you actually heat these carbonates, they may undergo thermal decomposition. So the key word here is may, right? So there are some metal carbonates that don't undergo thermal decomposition. So check with yourself, do you know what are the two that don't undergo thermal decomposition? Yeah, I'll tell you in a short while. So metal carbonate, when you actually heat them, they are likely to actually form a metal oxide and carbon dioxide gas. Okay, and this is going to be the trend that you must know. A more reactive metal will form a carbonate, a compound, all right, with a higher thermal stability. So more reactive, more stable to heat. More reactive metal, compound-wise, is more stable to heat. Okay, higher thermal stability means more stable to heat. So if it's more stable to heat, if I want to get it to decompose, it will take a longer time. Okay, and secondly, I could crank up the temperature. It will need a higher decomposition temperature. Okay, so now which are the metal carbonates that do not undergo thermal decomposition? The group 1 metal carbonates. They are very, very stable to heat. Okay, so sodium carbonate and potassium carbonate, right? In the experiments to actually compare, right, whether one metal carbonate has a higher or lower thermal stability, we may use this setup here. Okay, so the metal carbonate is being heated. We're going to close this test tube with or a boiling tube with this rubber bung here. And then we connect this to a delivery tube that is inserted into lime water. All right, so why? Because of the production of CO2. CO2 produced, you can test it, bubble through lime water, it will form a white PPT. Okay, so if let's say again I have two metals, iron and copper. So reactivity-wise, iron is more reactive. So therefore, the compound, which is iron 2 carbonate, would have a higher thermal stability, or it is more stable to heat. So essentially, again, it will take a longer time to decompose. Okay, to form CO2 and for CO2 to be detected in terms of then its formation of a white PPT when bubbled through lime water. Okay, and then for rate of reaction questions, you can also measure the volume of gas of CO2 produced per unit time. Okay, or if we let's say fix the volume of gas produced, calculate like measure the time taken, then for iron 2 carbonate, it will also take a longer time. Okay, so that's for the thermal decomposition of metal carbonates. And then the last one that we have under like reactive metals before we go over to what do you call that? Rusting of iron. Okay, so if we have ores, which are like mineral rocks that we can actually obtain from the earth, like through mining, okay, so the metals are in the compounds. So in order for us to extract these metals, okay, again, we have to relate them to the positions of positions in the Rayleigh series. Okay, so if you take a look at this first column, if we obtain the metals using electrolysis, first of all, you must make sure that these ores here in the solid state, they must be melted, okay, to be in the molten state. So if some of you have already started learning electrolysis in school, you have to actually heat the compounds to the molten form, all right? So over here, only the first four metals can be extracted from their ores using electrolysis. Okay. The bottom ones are actually possible so to be obtained by electrolysis. Because if you study electrolysis, you will know. Okay. However, this essentially is very expensive because we have to actually heat the compound such that it melts before it can conduct electricity. So we will not typically choose all these, choose electrolysis to obtain these metals from the ore, but rather we will use the other cheaper method, still uh, effective in the same way, which is heating with carbon. Okay, so again, this is where the position of carbon comes in. So to obtain zinc, iron, lead, copper, silver from the ore, you can actually heat the ore with carbon. All right, and this one would be an example of obtaining iron from hematite. Okay, so I have this to just show you hematite. Hematite is actually an iron ore. Okay, this is actually not in the syllabus anymore. All right, but I think some of you may have seen this in exam questions. So it's still possible for you to be tested when the question gives you enough information, right? And you will be able to actually explain with the information lah. So I just get you to focus over here. For example, if I have this iron 2 compound reacting with carbon, I'm going to get iron metal. So you see, I can actually extract the metal of iron and then CO will be produced. Okay. The other one on the right hand side, same thing. The iron 3 oxide, right, can also react with carbon to form iron again, extract the metal iron, and then CO will be produced. Okay. Moving on to the next question. Okay. Right. So for the thermal decomposition of metal carbonates, equal number, these two metal carbonates. So the X and Z are metals. Okay. X and Z are the metals. Some questions will just say X and Z are the carbonates. So just be careful of that. So the CO2 gas is produced, all right, and then the time taken for them to decompose is measured. Okay, so look at this. Larger value of time means longer time, right? So if it's a longer time for it to decompose, does this mean that it has a higher or lower thermal stability? Higher, okay? Higher thermal stability. So that means that metal is more or less reactive. Okay, more reactive. So here we can obtain our answer. Z is more reactive than X. Z is more reactive than X. Eliminate A and B. So now with the relative reactivity that we already have identified, so the suggested method typically for the more reactive metal, okay, we should obtain it from the compound using electrolysis. Okay, and that will give us the answer D. Okay. And question 8, we have these two compounds, the carbonates of two group 2 metals, which is barium and calcium. Right? So when these two compounds decompose upon heating, again, they will form CO2. So which compound will decompose first when this mineral contains these two carbonates? It's being heated. Okay, then explain the answer. So for this particular question, you have to link to the reactivity of metals again, and specifically linking back to the periodic table. Okay, the trends in the periodic table over here for group 2 metals is quite similar to group 1 metals. Okay, so we have learned, right, that actually for group 1 metals, their reactivity actually increases down the group. So lithium, not I, group 1, group 2, okay, lithium, sodium, potassium, rubidium, etc. So we also know, right, potassium is the highest or the most reactive metal in the Rayleigh series, followed by sodium. So just based on this, more reactive metal below in the group. Okay, so according to the positions of calcium and barium, calcium is the neighbor of potassium. Barium is two neighbors down below calcium. So therefore, barium is more reactive than calcium. So that will be your initial answer first. Okay. Then once again, what is the trend that we identified earlier? So the more reactive metal will form a compound with a higher thermal stability. Hence, barium carbonate will have a higher thermal stability. So it's more stable to heat. So now we can answer the question. So which compound decomposes first? Then that will be calcium carbonate. Okay. For the conceptual error here, so if you read this, barium is more reactive than calcium, hence it is more thermally stable than calcium. Okay, so this hence here, it here, you cannot make this link. All right, you must always go back to the metal carbonate. So for thermal stability, this will only be specifically referring to the compounds of the carbonates. Okay, it's not the metal. All right, so more info you need to specify the carbonate in the answer here also. Okay, so please take note of this. Okay, all right, and then the last part of this chapter would be actually rusting. Okay, rusting of iron. You may also encounter steel. So steel contains iron and carbon. All right, so in order for rusting to take place, we need to have oxygen and water. Okay, two ways to prevent rusting. First is barrier protection. Second one is actually more preferred using a sacrificial metal, okay, to protect iron. So what I have here in this diagram is a ship hull, HULL. So if you look closely, these are actually the small metals that are more reactive than iron. This would be magnesium, okay? And then it's basically sacrificial protection. So these metals will actually undergo corrosion in place of iron. Okay, so protecting the iron hull of the ship here. Okay, so how is a more reactive metal going to protect iron? Okay, so that is actually in question 9. If I have a small piece of zinc and lead in the two experiments attached to iron, always compare the reactivity. Okay, zinc is more active than iron. In this case, iron is more active than lead. Okay, Richard, this is the worksheet. Okay, so more reactive metal will undergo oxidation, and the less reactive metal will be protected. So for experiment 2, iron will react in place of actually lead. Okay, so experiment 2 is not what you want to do. If you want to protect iron, lead will be protected instead by iron. Okay, with this, our answer to this question would be A. Okay. Then for question 10, specifically when we say galvanizing or to galvanize iron, we use zinc. Okay, just remember like galvanizing zinc. So the zinc is the metal. Okay, so to prevent iron from rusting, so which statements are correct? Okay, so when iron rusts, atoms of iron will gain electrons. Is this true? So to form ions, right? If this is essentially iron 2 and this one is iron atom, no, it will lose electrons instead. Okay, because metal atoms have very few electrons, they will lose electrons. So we will not have 1, 2, 1 as our answer. So for this question, it would have been very easy to obtain the answer already if you actually chose the correct statement when you are very, very familiar with the gain and loss of electrons. This is D. Okay. So again, for sacrificial protection, even if the layer of the more active metal is scratched, the iron metal will not be rusting, okay, in the presence of oxygen and water. So this is the superior like advantage lah when using a more active metal that protects iron. Okay. Then for three, right, this statement here is a true statement, where it's basically this barrier protection. You form a layer around you have a layer of zinc surrounding iron, so that effectively is a barrier that prevents iron from being in contact with oxygen and water. Okay. Okay. So there are more questions, to a few more questions behind. I will just give you the answer. Okay, 11 answer is B, and then 12, the answer is D. Okay, these two questions are, I think, quite relatively straightforward lah, right? And then we will move over to energetics now. Okay, for energetics, if you are taking combined science, actually this chapter is relatively straightforward. So I'll focus more for those who are taking pure science or maybe even IP. Okay, but I'm not going into the calorimetry for IP, the syllabus. So energetics over here, the two terms that you must be very familiar will be exothermic and endothermic. Okay, so if we look at my example on the right side, for any exothermic reactions, they actually will give out energy. They will release energy. Okay. So I always tell my students, if you see X first, we think of it as exit. What exits is the energy. So energy is actually being released. So look at the arrows here. So when the energy is released, the box here is the reaction. So if I have, let's say, a solution, and the reaction taking place, I can measure the temperature of the solution, right? And this is the surrounding. Okay, I need to take note. This temperature that we're measuring is always the surroundings. And therefore, when the solution here, right, is absorbing this heat here, temperature goes up, right? That accounts for this increase in temperature. So this is only if you can measure the temperature of the surroundings, then the temperature will either increase for exothermic reactions or decrease for endothermic reactions. Okay, enthalpy change, these are the signs. Examples, please take some time to memorize if you have not done that. And then for thermal decomposition, perhaps to add on, of carbonates. So this is where we can also bring in just now what we've learned. Okay, under the thermal decomposition of carbonates in Reactivity series, where you basically heat the carbonate, if not, it will not decompose. So it is absorbing, the carbonates are absorbing energy. So that's endothermic. Okay. For melting, boiling, sublimation, condensation, and freezing, these processes here, I would say you can actually link to the packing of these particles. Okay, if you learn this, we learn this in KPT, kinetic particle theory. Okay, so consider, let's say, particles that are very closely packed, right? And if we want them to be further apart, so we have to actually overcome the attraction. Because particles that are very close, the attractions are very, very strong. Okay, and in order for them to actually become slightly further apart or to be away from each other, we have to overcome the attraction. Okay, so when we overcome attractions or for other reactions, we have to break bonds. Similarly, it's like if I have, let's say, HH molecule, and I want to actually obtain singular H atoms, I have to break the bond, okay, between the two H atoms. So the process of breaking bonds will always absorb energy. All right. So when bonds are formed, or when, let's say, the force of attraction become even stronger, energy will be released. So it's the opposite. Okay. So the syllabus does says that you have to describe bond breaking as an endothermic process, and bond making, or what we know more, like we see this more often as bond forming. Okay, this is exothermic. Right? Okay, so for question 13, this is the type of question where you must look carefully at all the equations and then identify, am I looking at bonds breaking or bonds forming, right? So as I mentioned earlier, if I have this H2 here, this is the molecule. And for us to get 4H, it's not a typo, right? It's actually four singular atoms, H, four of them, right? So we are breaking bonds. So in this case, also for oxygen, okay, then also please remember that this oxygen molecule, oxygen will need to share two electrons, so it's a double bond. And then it will form just O. So this will be bond breaking. I'll just use BB for short. Then this is actually endothermic, energy must be absorbed. Okay, so number two, this is actually the formation of bonds, because from the singular atoms we form, in this case, perhaps water vapor or steam. This will be exothermic. Okay, and the last one, more of the formation of attractions, right? The intermolecular forces of attractions under chemical bonding. Because we have H2O molecule, it's a simple covalent molecule. So the intermolecular force attractions over here, from the particles in the gaseous state to the particles in the liquid state, particles are actually now settling into a very closely packed arrangement, right? So we are actually like so-called forming the attractions, or yeah, forming attractions. And therefore this is actually exothermic. Okay, so exothermic 2 and 3, then that will be C. Okay. So for questions 14 and 15, also similar questions. Just more or less for these answers for C and D, okay, for these two questions, I just want to point out you have to know, be familiar with like equations or statements that involve neutralization. Okay, H plus and OH minus is neutralization. Acid plus alkali, also neutralization. So you have to know that this one is exothermic based on the list here. All right, so be very, very familiar with this and do memorize lah. This will help you to answer all these questions more quickly and then move on to other tougher questions. Okay. And then for the next one that we have, for chemical energetics, okay, we will need to explain qualitatively, right, the overall enthalpy changes. So in terms of just energy changes associated with breaking and forming of bonds. All right, so this changes and changes in energy, it is essentially absorption of energy and the release of energy. Okay, so this is the answer template that we have in our notes. Copy and pasted here. All right. So this will be the exact way that you should answer the question. Okay, so we will look at the questions to apply this answer template. Right. So overall, how do I know if a reaction is endo or exothermic? We look at typically the enthalpy change values. So questions will tell you, okay, this is the enthalpy change, it's negative, right? Sorry, then we'll put this here. Then that means that it is exothermic. So we work backwards. So why is it exothermic? Then we link it to actually because there's more energy released, right? Exit than energy absorbed. So then when we do a comparison, energy absorbed will be less than energy released. Okay. Then just to take note of this, so the blanks here, reactants and products, specify if we know what they are. So most of the time questions give you very specific scenarios, right? So just specify. Then I believe some schools they are a little bit more particular. You might need to also specify the bonds. Okay, so I'll just show you um how it is going to look like. Specify. Okay. So we move over to the examples. Wait, okay, wait, one more thing first. So which is the energy profile diagram lah. So you should be able to confidently draw the energy profile diagram already. Okay, so do take note of the energy level diagram. So this is the one without the activation energy and this this curve here. Okay. For energy profile diagram, so typically this is more tested, usually takes up about 2 marks. All right. So take note of the axis, energy against progress of reaction. It's not time. Right? And then we have the reactants. Always remember to also write down, okay, the chemical formula. Then from here, always have an activation energy pointing from the reactants to the highest point. Okay? So do not draw something like this for the enthalpy change. Sorry, the activation energy. So this is not correct, right? It should be from the reactants to the highest point. Right. Now, I just want to point out, if you're doing this, it's not correct, you'll get penalized. Okay. So you may think you are showing it correctly, right? But please, the triangle means, triangle H, it means you haven't learned this before yet. Uh, triangle means change. It's actually delta. Yeah. Okay. Okay. So don't worry lah. You'll come to this again. So I think you're just using this time to maybe have a head start, right? Okay. So H means enthalpy, and then what enthalpy also means actually is just energy. Okay. So enthalpy delta. Okay. For the Greek letter lah. So this means change. Okay. So change enthalpy. Enthalpy is energy. Actually, this is energy change. Okay. Energy change, enthalpy change. All right. So I was mentioning this arrow here, should point from reactants and then to the highest point, like that. Okay, so EA means the activation energy. I'll explain what's that in a moment in question 16. All right. Okay, so now for Kriti then, reactants to the products, now it actually shows us that there is an overall increase in the energy level. Reactants to products. So this is effectively the enthalpy change. Okay, and it's a positive value because it's going upwards. So for reactants to products, now we are pointing from reactants and then it's going downwards. So if I explain this verbally, it means the reactants, right, essentially like lost energy, then therefore the product's form will have a lower energy. So enthalpy change is going to now be negative because it is going down, pointing downwards. Okay, then this will be the energy profile diagram. I will discuss a little bit further in detail when we do the exercise that brings in energy absorbed, energy released. Okay, so now what is activation energy? All right, if you read this statement here in this question, it is the maximum energy the colliding particles must have in order to react. Okay, this statement is false. This is the minimum energy instead. Okay, this is the definition. So activation energy is the minimum energy that particles need to possess in order for them to form a reaction, which is actually this amount of energy. Okay, so if let's say reactant particles don't have enough energy, they essentially cannot form products, right? So one is not correct, and then same thing lah. Okay, 2 and 3 will be the answer, but let's also look at the two statements. So during an endothermic reaction, so once again, there's the net absorption of energy, right? So thus, thermal energy, heat is taken in, absorbed. Okay, so absorption, absorbed, taken in. Then as a result, okay, so again, if I just show you this example here, so this is the reaction. So if the reaction is absorbing energy, look at the arrows. Then if let's say let's say this is in a solution, right? I can only measure this temperature of the surrounding solution. So when energy is absorbed from the solution itself, the temperature will decrease. Okay, so that's why this is true. And then the formation of bonds is exothermic, also true. So answer is D. Okay. Yeah. For question 17, when we encounter the word combustion, combustion means to burn in oxygen. So you will be expected to know that you have to have oxygen as the reactant. Okay, and combustion is always exothermic. So again, this is something that we have to memorize on top of the neutralization reaction being exothermic. Okay, and again now if we compare all the statements here, all the options here, whenever we have exothermic reactions or endothermic reactions, we always look at the energy involved. Okay, we compare the energy involved in the breaking and the forming of bonds. We will never compare just the bonds broken and bonds formed. Okay, let me just explain to you what is this one and two, A and B statements here. So in order for us to look at these two statements, we have to look at the structures of the reactants and products. Okay, so methane has this formula. You will learn this again in organic chemistry. Okay, so methane, CH4, carbon is singly bonded to four hydrogen atoms. Then I have two oxygen molecules reacting. Oxygen exists as two atoms connected via a double bond. Then carbon dioxide, sorry, I'll just put arrow here. Carbon dioxide is CO2. This is the structure, right? That you would have drawn this before in chemical bonding, covalent bonding, and this is water. Okay, so if you take a look in our reactants, we are actually breaking four CH single bonds, 1, 2, 3, 4. We are breaking two oxygen-oxygen double bonds. Okay, so the process of breaking bonds here is settled. And then now the formation of bonds, we are going to form this carbon dioxide contains two carbon-oxygen single bonds. And then in water, I have two OH single bonds, but with the two in front here, I times two. So it'll be a total of 1, 2, and then 3, 4. Four OH single bonds. If I get us to compare now, if I just look at the two statements here, we are breaking total of 6 bonds. We are forming a total of 6 bonds. So technically, we are breaking the same number of bonds as what was formed. So that's why A and B, this type of statements are actually quite superficial. All right. So the number of bonds broken and formed doesn't mean anything. We have to now include something called the bond energies. So we will discuss this later in the next page. Okay. So that will then help us to actually quantify the amount of energy absorbed and released. So some of you would be familiar with that type of question already. Okay, so anyway, exothermic, right? Energy will be released. So energy is released only during the formation of bonds. So therefore, less energy is involved in the breaking than in the forming or the making of bonds. Okay, for question 18, so now applying the answering template to this part here. So if I have hydrazine reacting with oxygen to form water and nitrogen, if you haven't seen hydrogen before, this is the structure. So nitrogen atoms can actually form, rather they can share 3 electrons because they have 5 valence electrons. Then hydrogen will share 1 electron. So this will be the structure of hydrazine. Okay, oxygen once again double bond. For water, H2O. And then for nitrogen, this one we have a triple bond. Okay. So when we look at why this reaction is exothermic, okay, so enthalpy change value tells us also that's exothermic. So now in terms of how to explaining here, we will bring in the energy associated. All right. So let's just say I want to talk about the formation first of bonds. So remember, energy is actually being released when bonds are formed. All right. So now the bonds are formed in which products? Okay, so the products here are actually water. I guess water vapor or steam, gas, and then nitrogen. All right. So minimally state that the bonds are formed in H2O and N2. But there might be some schools that will require students to just refer to the equation to look at the mole ratio. So there are actually 2 moles of H2O and 1 mole of N2 over here. Okay, we keep this comparison aside first, and then the energy is actually being absorbed to break the bonds. So during the breaking of bonds, and then the bonds in hydrazine, this is the reactant, so N2H4, and then we have oxygen O2. Okay, so from the equation, the mole ratio here is actually 1:1. All right, now we can do the comparison. So exothermic reaction, if we work backwards, it means that there's a net release of energy, and that is because there's more energy released than energy absorbed. So then we have this comparative term here. Energy released is greater than energy absorbed. All right. The last part here. So there's a net release of energy, I would say, from the reaction. Okay. Change the others in case my battery runs out. Right. So for B, let me just show you how to draw this quickly if you have not learned this before, or you want to take this time to refresh your memory on how to draw the graph. Okay, so I would say you draw the energy axis first. Okay, so for the axis, we have energy and then kilojoules per mole. All right. Because it's exothermic, so the shape of the graph will be in such a way that the reactants here, or I'll just put as RXT, the reactants will have a higher energy level than the products. Because why? There's a release of energy. So decrease in the energy level. Okay, so then we'll just draw this curve here. But before I draw the curve, generally I tell my students to actually write down everything that they see in the equation first. So if I have N2H4 gas and then O2, right? So I make sure I have enough space for all my reactants first. Then I proceed to draw the remaining parts of the curve. Okay. Then exactly where the reactants are, I draw the dotted lines, I extrapolate, find the highest point, and then we'll have this as the activation energy. So done. And then you may also just extend this, but please use your ruler. Okay, and pointing downwards, this is the enthalpy change. And then finally, we also fill in the products of H2O and N2. Okay. If you like to, you can also just shift this outside a bit more lah. Don't overlap. Okay. Uh, if we know the value, -622, let's also write that down in our answer, in the diagram here. Okay. And one last part, don't forget, this is your progress of reaction axis. Okay, and that will be 2 marks. Right? So secure the 2 marks here. Okay. So I will upload the answers in the, let me see. Okay. If you need the answers, you let me know. Okay. Uh this will be the, yeah, same thing. Okay. Okay, moving on to the last few parts of this chapter. So the calculation of enthalpy change. All right. We have to be very familiar first with the structure of the substances. So I showed you some examples earlier over here. Okay. So to know like what type of bonds are present, type of bonds means specifically single, double, triple bonds. Okay, the type of bonds here. So whether is it single, double, DOU, or triple bonds. Okay, and also the number here. Then how to calculate the enthalpy change? We add up, so this summation sign, add up all the bond energies of the bonds that are broken, and then we subtract the summation of all the bond energies of the bonds formed. Okay, cause why? This is actually energy absorbed to break bonds. Absorb energy, right? Positive sign. And then energy is released during the formation of the bonds. You have a negative sign here. So overall, this is where the minus sign comes in here. Okay. And then for your copy, I'm so sorry. Please change this to 19 and 20. I've added a question like halfway through, then I forgot to change this up. So for question 19, this type of question is where the question gives you the bond energies of all the bonds, and then you are supposed to find enthalpy change. If you are new to this bond energy, basically it's just a value that is actually uh, telling us how strong or how weak the bond is. Okay, so if I get you to look at the table below, NN single bond versus NN triple bond, right? NN triple bond needs a lot more energy to be broken or formed. So the bond energy of NN triple bond is 945. It's a lot higher than NN single bond. So likewise, I can say that this triple bond is therefore stronger than this NN single bond. Okay. You'll see that in the next example, question 20. So bond energies of most bonds are given, and then for the enthalpy change also given. So instead, you calculate an unknown bond energy. Okay, so we will see that example in a bit. Okay, so for question 19, hydrazine reacts with fluorine to form hydrogen fluoride and nitrogen. Right. So whenever you encounter this, what we do is we'll have to identify what are the bonds present. So this is hydrazine, then this one is fluorine. We also put in the stoichiometric coefficient here. Okay, because that also tells us the number of bonds that are broken and formed. And then for nitrogen, it's this triple bond. So once we are able to identify all the structures, okay, we can then look at the reactants first. So in the reactants, what bonds are we breaking? We are breaking one NN single bond, and then we are breaking 1, 2, 3, 4, 4 NH single bonds. Okay. In fluorine, we are actually breaking 2 FF single bonds. Then that's it. All right. So now identify the number of bonds broken here. Then we will just look at an N single bond, one of it. So this is the amount of energy absorbed to break the bond, 163. And then going on to the next one, 4 times of NH single bond, 4 times of 390. Okay, and the last one, 2 times of 158, fill that in. Okay, that will add up to 2039. So you do the same for the bonds formed. What are the bonds that we are forming? So in the products, we have 4 HF single bonds and 1 NN triple bond. Okay, and then we can key or like identify the bonds again. So this one, 4 times 565. And then we add it to 1 of 945. Okay, just like that. So now overall in the reaction, energy is absorbed first. Right? Now I just show you in the reactants of N2H4 reacting with 2F2, maybe I'll just show you here also. Energy is being absorbed. Okay. So this increment of 2039 kilojoules of energy begins here, so that we will now just have a total of 2 N atoms, 4 H atoms, and 4 F atoms. If you see after breaking all the bonds, if you break already, then these are all the singular atoms. Okay, and then now when energy is released, in our calculation, 3025. So the arrow that I'm going to draw will have a longer line here, because 3205 kilos of energy will be released. So, but when we write down the word release, we don't put the minus sign. But in my sketching here, I have to put the minus sign because it's going downwards. Okay, and then as a result, these are the uh, products formed, which is 4HF and then 1NN, N2 molecule. So if you can see now, the big picture is this. This would have been the energy profile diagram curve. This go up, come down, and this. Then overall, the difference here, right, between the reactants and products would exactly be just taking energy absorbed minus energy released, and then that will give you this overall change of negative 1,166 kilojoules of energy. Okay, so this is if we bring in the energy absorbed and released into this big picture, then now you can like appreciate why the energy profile diagram looks like that. Okay. Uh, one more thing. So whenever you have, let's say, a value like enthalpy change is positive, so in another example here, please put the plus sign. Okay. So you need to put the positive sign for endothermic reactions. Okay. So don't ever forget the plus sign. Minus sign quite intuitive, but if it's a positive value, please put the plus sign. All right. Okay, and then the last type of, sorry, wait, before that. So I'll just go through using my solution here for question 20. Okay, so uh, just now I mentioned you already. In the MCQs, if we look at the word combustion, all right, so just tell ourselves, I'm burning in the presence of oxygen. So even though the question didn't tell me, I must know. All right, so balance the, write down first, right? So the hydrogen reacts with oxygen, undergoes combustion, and then it produces water and hydrogen. So that's how I obtain water and N2, H2 and N2, and then you'll balance by putting 2 over here. Okay, so B is the question that I mentioned to you. I will not know the bond energy value of one of the bonds. But instead, what the question will tell you then is the enthalpy change of the reaction. So the way you work out the question is actually similar. So energy absorbed to break bonds. First, identify what are the bonds broken and what are the bonds formed. Okay, so these are the bonds broken. Once again in a hydrazine here. And then for oxygen, 1 molecule. Then formation of water, you have 4 OH single bonds and 1 NN triple bond. Right? Then look at the values, write that down, and then you will have this in terms of X first. Oh, sorry. What is this X? Okay. So instead of writing down bond energy of NN single bond, for me, I'll choose to let this be X. A bit like algebra. So it's easier for me to also use to solve later on. All right. Then after that, energy released, same thing. Find out the the bond energy values of the the bonds that are being formed. Okay, so now energy absorbed is this, energy released is this. Then we can actually just use the formula energy absorbed minus energy released. Okay, minus 2797. Then it's equals to enthalpy change. So then you will be able to actually obtain X to be 113 kilojoules. Okay, for these bond energies, they don't have a plus or minus sign. So the plus or minus sign is something that you put in if you know energy is being absorbed to break that bond, you put the plus sign. If energy is released from the formation of that bond, then you put the minus sign. Okay, so in general, that one has no sign involved. All right. Uh, Now we move on to the last portion. Um, I have one student who actually asked me. That's why I chose to uh put this concept here. Okay, so the conversion of kilojoules per mole to kilojoules per kg, or sometimes it could also be kilojoules per just grams. In the question later. I just get you to actually think about an equation. Okay, how do I convert kilojoules per mole to kilojoules per kg, for example. Okay, so if we see kilojoules per mole, right? If I want to have an equation to convert them, then I should change this. Kilojoules per kg. I want to change to kilojoules per kg from kilojoules per mole, right? So, this is obtained when I have this units of kilojoules per mole, and this one is kilojoules per kg. So I write this in the form of fractions because it's easier for us to, I guess, view it. Okay. So you should be able to tell me what is in the numerator and denominator here. So kilojoules is staying, right? So I actually don't want moles, but I want kg now. So I think y'all can tell me that this one at the top should be moles, right? In other words, like we sort of cancel out. And then we sort of put in the kg here. Okay? So what is this? What is moles per kg? If I get you to think of the opposite, when you multiply by a fraction, if I work backwards, I can say that I can also divide by a fraction. So here I can divide by this fraction of kilojoules per mole. Okay, because right, you change to times, then you get the reciprocal. Okay, so now we are getting closer. What is this kilojoules per mole? Kilograms per mole. 1 kilogram is actually 1,000 grams, right, per mole. Then I want you to see that this grams per mole here is actually just the mass of 1 mole. And it's actually known as the molar mass. The molar mass of any element or any compound can be obtained from the periodic table here. Okay, we link it to the AR here, or the molecular mass of the compound. All right, so if you look at this big picture here, if I want to actually convert kilojoules per mole to kilojoules per kilograms, I need to divide by the molar mass of the substance, and then multiply by 1,000 if we have to convert to kilograms. Okay, so over here, if I have this question involving hexamine, so this is a solid fuel. Some of you, maybe if you've gone to OBS, you would have used it for cooking in the mess tin. Okay, so this is the enthalpy change given to us, negative 4,200 kilojoules per mole. So what this means is I burn 1 mole of hexamine, 1 mole. It will actually, minus sign means release 4,200 kilojoules of energy. Okay. The question wants us to actually calculate the energy density of hexamine. And what this means is actually, I don't want to burn 1 mole. I want to burn 1 gram of fuel. Okay, kilojoules per gram. Okay, so how do we do this? I'll show you the faster way. So if I want to solve for kilojoules per gram, right, essentially, if I have kilojoules per mole already, the minus 4,200, I just need to multiply by moles per gram. So in how we looked at this earlier, right, this is the conversion here. So multiplying by moles per gram means to divide by the grams per mole, which is the molar mass of hexamine. Okay, so this molar mass here, I just change this around. This is the molar mass, which is the MR that you are familiar with. Okay. Given that or rather when we do calculations, so add them together, we get 140. So we can just take negative 4,200 divided by 140. Okay, and then we'll get this negative 30 kilojoules per grams. Okay, so this is using the formula that we derive from. If you don't want to use the formula, you can also do that. What you do is you find out the number of moles in 1 gram of hexamine. Because I want to burn one gram instead of 1 mole. So in other words, we will find the number of moles by taking mass over molar mass or mass over MR, which is like 1 over 140. Okay, this is the number of moles here. So if you see this, 1 over 140 is the same as dividing by 140. So then, for my enthalpy change of negative 4,200 kilojoules per mole, I multiply by 1 over 140 moles, which is then for the number of moles of 1 gram of this hexamine. So we will be able to cancel away the moles, and then what will remain is kilojoules and then per gram. That's why the units are still going to remain here. Okay. So for this energy density, we'll put in the minus sign. For question 22, whenever you see this type of question, calculate amount of energy released, right? Always omit the negative sign. Okay. So the enthalpy change here for the combustion of ethanol is in grams. 1 gram burns to release this amount of energy. So if I, let's say, look at 100 moles of bioethanol burning, okay, so what you need to do first is to go and convert this um, enthalpy change in kilojoules per gram. You find it in kilojoules per mole first, right? So what is it equals to? So we will need to take kilojoules per gram. So look at the unit. This one is divided by grams already, right? So let's multiply by grams per mole. If you see this, cancel, you get kilojoules per mole, kilojoules per mole. Okay. So this negative 30.5 times this one for ethanol, the molar mass of ethanol is the MR. So 12 times 2 plus 5 plus 16 plus 1, this is 46. Okay. This ethanol is also an organic compound. You will also learn this in organic chemistry. Okay. And then overall, what we'll have over here, wait, just let me quickly key that into the calculator. So this is negative 30.5 times 46. Okay, so negative 1403. Okay, so this is the answer in kilojoules per mole. Oops, yeah. Okay, so 1 mole releases negative 1,403 kilojoules of energy. So right now, when we answer the question, amount of energy released when 100 moles of this ethanol burns. I'll show you the units here. This is in kilojoules per mole. I want 100 moles. I multiply by 100 moles. I'm going to cancel out the moles unit. And then that's where I will have 140,300 kilojoules. Okay. And this is not the correct answer because when I write down the word released, I must omit the negative sign. Okay, so this is something that you must actively erase away. Okay, and then you will get this answer here. So energy released, don't write down minus sign. Enthalpy change can be plus or minus. All right, then that will be all for this session. Okay, if you are able to do so, like I mentioned to you earlier, you can drop us a review on Google. Okay, then I was saying, let me see, there are 35 of you. Okay, so I'll choose 5 of you. Um, after you give the review, it might take a few days, so I will contact you via the sign up form that you have. So either your handphone number or your email. So I'll get your mailing address basically. Okay, then from your mailing address, I will send you a copy of electrochemistry notes. So this is the next chapter. It's quite a huge chapter in the Sec 4 syllabus. Okay, and then I'll give you a piece of our laminated periodic table that has quite a number of good information in our cheat sheet. Okay, over here. It looks like that. So it will be laminated for you. If you haven't gotten this before. Yeah. All right. So okay, for those, if you want it, right? If you want this set of worksheet with the intros, you give me a while, I'm gonna send it to you on this chat here. Okay, so wait, I'll just get you to do this. Let me export this first. Okay, you just hold on a while. I will export this to my laptop and I will send it to you. Okay, yeah. So once you've completed a review, you can go off with it if you have no questions for me. Okay. All the best for your WA, or uh if it's just a a, a crash course for you if you haven't learned, then I hope this is helpful in your revision for exams in the future.